There we go. All right, so that should work now. Tomorrow. All right. Another 10-second delay or so there. But today, we're going to start on what we're going to cover for the next 2 weeks, which is dynamic programming. And I'm going to do this by giving you a motivating example, first of all. But first of all, why is it called dynamic programming? There's not really a good reason. Dynamic was a fancy marketing term when it was developed. Literally, it was this guy that came up with the general idea, the general approach in the 50s or 60s or whatever, and then he basically had to sell his research to the Department of Defense or whoever the hell he was working for, and so he had to come up with a pizzazzy name, right? So he called it dynamic programming. Do not ask me the history there. You can go ahead and look at the Wikipedia page on it if you really want to, and find out what that means. It really is nothing to it, though. The actual problem-solving technique and approach is nothing more than a divide and conquer approach that you've already seen before, where you can divide a problem into 2 subproblems, solve each one of those subproblems, and then combine it into some sort of a solution. It lends itself to a recursive solution. But then what you do is you take that recursion and you realize and you reformulate it so that you're not making any recursive calls. Instead of you're doing what's called a tableau, basically. You're filling out a table. So to motivate that idea, what I want to do is I wanted to go back to something that you've probably seen before, binomial coefficients. So n choose k. That's the number of ways that you can choose k elements from a set of size n. Now, normally this has a closed form solution involving factorials, or you can use Pascal's identity. Pascal's identity has you doing a recursive call to add up n minus 1, choose k minus 1, plus n minus 1, choose k. Why do we call this Pascal's identity? Well, he came up with it. What is it related to that you've seen before? Pascal's triangle, exactly. And so you call it Pascal's triangle. And we'll see this coming up later on here. There is a base case here, but if you have n elements, how many other ways are there of choosing n things? 1. You choose them all. If you have n elements and you choose none of them, how many ways are there of doing that? 1, because you're basically formulating the empty set. Right? Do we need any combinatoric review here on this? Or not? No? Okay. Then let me go ahead and show you a demonstration here in Python of Pascal's identity, right? And running Pascal's identity. Okay. So I've got this set up for choosing 10, choose 5. I want to know how many ways there are from a set of size 10. So a class of 10 students. I need to choose 5 of them to formulate a team or something like that, right? How many ways are there of doing that? Well, I've already set up the answer here to make sure that this works with Wolfram Alpha, 252 different ways. The way that I have computed this is I've computed the base cases. When you're choosing just as many things as you are, as the things that you have, or you're not choosing anything, you output 1. Otherwise, you do this recursive Pascal's identity, right? And I output the result here. So just making sure that this works. Let's come over here. Python 3 demo. There we go. All right, 252. Okay. So it works. At least I'm convinced that it works. Let's go ahead and try to compute this for 100. Choose 50 though. All right. So that might take a while. Let me come over here and ask just Wolfram Alpha, what's the actual solution here? That didn't take a while. I don't know, what is that, 100 octillion or so, okay? Python will be able to support this because Python 3.6 and above or whatever it was will support arbitrarily large values. how much longer should I wait? Whole class? Okay, so like an hour.
What was the actual version again? Sorry.
Right there.
Okay.
So it should only be doing, you know, several octillion computations, right? So how long will it take?
Probably longer than
Tens of thousands of years.
Fred.
Okay, let's kill it.
I was off.
Right.
by-
Yeah, several orders of magnitude off there. All right. So what is the solution? You know, when I usually present this, say in Computer Science 1, we do Fibonacci or we do binomial coefficients here. And we come up with a technique to improve the recursion. The problem here is that the same recursion is being computed over and over and over again. Just like with like the Fibonacci sequence, if you try to call Fibonacci of 100, you'll end up computing Fibonacci 50 billions and billions and billions and billions of times over and over and over and over again. So what's the solution?
You can save all of the ones we
Save off all the values into some sort of a cache, and then instead of doing the recursion again and again and again, look it up and see, has it already been computed before? And if so, use that. Does anybody remember what that's called? Memoization, exactly. So let's go ahead and implement that version using memoization. I'm going to call it binomial mem, right? And I'm going to be passing in a cache each and every single time. We're not to dynamic programming yet. I'm just trying to remind you of what this looks like. So I'm going to go ahead and use n and k as the key here. Normally, if this were a different programming language, what I would do is I would set up a pair or something like that. Well, that's what I'm doing here with this key, right? The cache could be a two-dimensional array where you store stuff in, but why do that when you can use a tuple in Python as your key in a dictionary, and your cache can end up being a dictionary instead of a two-dimensional array. In fact, can you have two-dimensional arrays in Python? I think it ends up just being a list of lists, right? It's not a true two-dimensional array, right? So I'm going to use that as a key. Now, if the key is in the cache already, in other words, it's already been computed, then simply just use it and return the cache of the key. Right? Otherwise, and here is where I'm going to do this base case right here. So elif, right? N is equal to k, or k is equal to 0. Then I will go ahead and return 1, but before I do, what should I do? I should put it in the cache so that I don't have to recompute that value ever again. Otherwise, else, I have this thing right here, okay? So, result is equal to, I have to pay for the recursion. But instead of immediately returning it like I did in this first version, what will I do? I will go ahead and save it off into the cache key. Sorry, can't type today. Result. And then return it. There we go. Questions?
Oh no, I was just gonna say, what if the key isn't 1, but that's where it expires even if
Yep.
it isn't else?
Exactly. And I'm going to have to call this version now as a recursive call. Right? So let's see if this improves our game any. All right? I'm going to come back over here. Actually, let's go ahead and make sure that it is actually correct, first of all. Remember, 10 choose 5 is going to be? Oops. I need to pass in the cache there. Once I've done that, then 252. Okay? Excellent. So now, 100 choose 50. Instead of taking tens and tens of thousands of years, let's find out if this works instantaneously. And it's going to be 100891 blah, 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 ending in 256. I'm convinced that it's also correct. Let's keep going. So if you can compute 10 choose 5, 100 choose 50, surely you can compute 1000 choose 500. What happened? Yep, stack overflow. Why? Maximum recursion depth exceeded in comparison. What was happening here? You wanted to go 1,000 or so levels deep in your recursion, right? Now, overall, you are still pruning things out with this memoization technique here. You're not that if we were allowed to go that deep in the recursion, then this would basically, I mean, it might be a little bit longer noticeable computation time, but certainly it would get the correct answer, and it would not take tens of thousands of years. The problem here is that even 1,000 levels deep, right, in the recursion, that's not even allowed in Python? What the hell, right? This is a small number. I should be able to compute something that's a 1,000 things, right? But it's because I'm using recursion still in this memoization technique that I'm hampered. So, ideas. I could create an in-memory stack and then simulate the recursion, right? Instead of abusing the call stack. Okay, let me go ahead and we could make a stack that stores an n and a k, and then make cache into a global variable if you want to, so that we're not making, actually a local variable, I guess, right? And so that we're not making recursive calls anymore. But before we do that, let's go ahead and see what happens. Look at the cache a little bit here. So print cache. So I'm going to go back to 5 choose 10 so that this is actually manageable, and we will actually be able to look at this and see what this looks like. I don't know how to print this any nicer, but you can see 5 choose 0, that's 1. 4 choose 0, that's 1. ... Right? 10 choose 5, that's 252. There's the final answer. If I were to take all these things and move them out, what would it look like? What's one possibility that it would look like? It could. How would it look like a graph? That's actually an interesting way of putting it. It would look like Pascal's triangle, right? Now take that triangle and move it like this. I said that we were using a dictionary here, a map. What else could we have used? N's over here, K's up here. N's and K. Right? And each one of these is going to be an entry of N choose K. I'll save that for later here, though. But what are the indices going to look like? So let me go ahead and label it as I and K. That looks nice. There we go. All right, and let me get rid of N over here and give myself some more room. What values will it run from? 0, 1, 2, 3, 4, ... up to N. All right? And then I'll put one more over here, N minus 1. These are all the values of I. All right? Over here, these are going to be all the values of K. 0, 1, 2, 3, all the way up to K. Right? This is my cache. I could have treated this as my cache instead. A table, or if you want to get fancy, a tableau. Right? And that's what they usually call these things. Right? So let's think about Pascal's identity, and implicitly here Pascal's triangle as well. When these two things are equal, when n is equal to k, that value is 1. What does that look like here in the table? On the diagonal, they're all 1. ... Now, at some point, because n is usually much larger than k, then you're going to hit some point here. I'll go ahead and shorten this up. That you end right there. What about the values up here? What does that correspond to? 1 choose 4, for example. Does that make any sense? Or 2, choose 10. Nope. So these are what? Invalid. Right. All right. What about the other base case over here? N choose 0. Where does that correspond to over here in my table? N choose 0. It's this column right here. Okay? So 1, 1, 1, 1, dot, 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 1, and 1. Those are my base cases. Now, look at Pascal's identity again. N choose k is equal to n minus 1, k minus 1, choose k minus 1, plus n choose k minus 1. Make absolutely sure, I'm pretty sure that that's it. Ah, no, I did screw up. N minus 1, choose k. There we go. There's Pascal's identity. I've just copied it over here. Now, what does that look like with respect to this table? Think about n, choose k. Right? That's the one we're interested in, by the way. The last entry down at the bottom right. That's the actual answer, n choose k. That is equal to n minus 1, choose k minus 1. Where is that in the table? N minus 1? Well, you go one level up, right? And then k minus 1, where's that? 1 over. So over here is n minus 1, k minus 1, choose and choose. What about the second one there? N minus 1, choose k. Where's that going to be in your table? Right above it. Right. So this one is equal to this one plus this one. That's Pascal's identity, exactly. Right? This identity holds for everything. So if I want an entry over here, for example, this entry, whatever this is, all I have to do is look above, and then above and to the left, and take these two values and add them together. And then put that value in that cell. That suggests a non-recursive way of doing this. All I have to do is fill out this table, right? What order do I have to fill out this table in? In order for this value to be available, the one above it and the one above it and to the left has to be available. Top left. Well, you could. A good point. Until you reach the diagonal, at which point don't do any more. Till you reach the diagonal. 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 Right? Let's fill it out a little bit here. What about this one right here? You look one above, and you look one above and to the left, and what value is that? 2. There are 2 values right here for the third row, or the fourth row, I guess, since you start at 0. What is this value right here? 1 above, and 1 above and to the left, so that's going to be 3. What about this value right here? 1 plus 2 is 3. Predict the next row for me. 4, 6, 4, dot, 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 right? All you have to do is start at the top left and work your way row by row by row, right by row. By the time you get down to this last one here, guess what? You've got your answer, and that's where you stop. Help me to develop this code then. So let's go ahead and create a new function, def binomial and dynamic, for dynamic programming solution, n, k, and here I don't need a cache. Why? At least I don't need a cache because I'm not going to do it recursively. Instead, I can create my own local cache here. And I'm still going to use a dictionary, by the way, because that's Python. Right? But if this were Java or something else, I would create an n plus 1 by a k plus 1 sized table. Why plus 1? Because you start at 0, but you go all the way up to k. You start at 0, but you go all the way up to n. So that's the size. I'm going to cheat a little bit here and use the fact that Python, you can use a tuple as a key, I and j, so row and column, and like I did up here. Right? Here's my key. All right, so help me out here. How would you go about doing this? Well, write this loop. I, and I called this, oops. I called this k, but I shouldn't have. I'll call it j, so as not to confuse it with this k over here. So for I running from 0 up to n, for j running from 0 up to potentially k, but like you pointed out, stop when what? When you hit I. Right? Okay. That suggests to me 2 for loops. Right? For I in range 0 up to n. Is that going to work first of all? How does range work, Pythoners? What will be the last value? It'll be n minus 1. It stops short by 1, so I want to go up to and include n. Right? All right, for j in range 0 up to, yeah, that one's going to be a little bit confusing, right? Because when we get down here, does this triangle continue past k? Nope. So I stop when I either hit k or when I hit I. Whichever one's shorter, or because these are numbers, we call them whichever one is minimum. Right? So minimum of I and k. And then here again, plus 1, because you want to go up to and include k. You want to go up to and include I. All right? And now all I have to do here is the base cases, right? If this is true or this is true, then it's going to be a value 1. Otherwise, it will be Pascal's identity, right? So if j is equal to 1, or 0, excuse me, or I is equal to j, that's on the diagonal, then the value here is going to be 1. How do I do this key? I do it like I just did up there, I and j. I throw, jth column. Right? I don't know, does anybody else appreciate that? Normally, if this were another programming language, what would I have to do? I of j, right? But because this is Python, I can create a tuple and do something like that. I can see the argument both ways, yeah. But it is kind of cool. I like it. It's a nice feature. Yep. Well, tuples in general are nice features, and I wish more languages had them. That's the one thing that I really love about Python. If you want a tuple, you can just create one really, really quick, because it's built into the language. Right? Else, c sub, and then here's my key again, ij, is equal to c sub something plus c sub something. What is that something? That is n minus 1, k minus 1. But in terms of our loop here, it's going to be I minus 1, j minus 1. Right? The one immediately above and to the left. Right? So the one immediately above to the left. And plus the one immediately above and then in the same column. So c sub I minus 1, j. Okay? At the end of the day, what do we return? After we've filled out this table, this tableau. Which entry are we interested in? And choose k. Exactly. That was our input. Okay? Let's see if this works now. Yeah, go ahead. Is there a problem? Oh, okay. It's easier to just change that to a C. C for cache. Yeah.
Should we even go through the trouble of making the ones that are in the
Like this up here. I didn't go to the trouble
No,
of
no, no,
defining
no.
those.
I mean, if we only need the ones that are essentially like,
Well, technically, this is the only one we really need.
I know,
But
but
we need these to compute it using Pascal's identity. You're right in an observation here that you only need the row right, immediately above it. So if you want to, after you're done with this row and then you're computing this row, you can throw all of these rows away. Who cares?
well, no, I was actually saying we only need because we only need to figure out k choose n, we only need the two above it.
Right.
So we would only need the four that those would correspond to. We don't need to compute any other elements on that row.
But then you're right back at square one where you're going to have to do some sort of recursion, because you do need more than one. I mean, you're going to need everything down here to do the next row, because you'll need this one, this one, this one, this one, this one. So you'll need the entire row right above it. Do you have a different perspective?
I think, so we only compute like a trapezoid of it, so we don't need that bottom left corner triangle.
Bottom
Yeah, that's
like
what I was.
bottom left corner triangle?
So sort of like how we don't need to compute the stuff up here. Why do we need to compute the stuff right here?
Well, what's this based on? This one is based on this one and this one.
Right.
And so what's this one based on? This one and this one, right?
Right. But why would we need it?
I think I see what you're saying, yes. There's some values down here that you may not need because as this cascades up, right, you don't need, so the trapezoid being this thing, this type of trapezoid.
Right.
Okay. Yeah, I can see that, yeah, definitely. Now figuring out the indices, good luck. I think that the code that we just wrote is a lot simpler than
That's true.
saving on some amount of work over here.
Alright, I just wanted to see.
But yes, yeah, you're absolutely right that you probably don't need those values. But let's see if we're actually correct on anything first of all. Right? And we won't print out the cache anymore. Right? 252 still. What was 150? Does anybody remember that? That looks like it. I thought it started with 100 and then it ended with 256. And now here's the test. 1050. The tableau would be at most size 500,000. 500,000 numbers, that's nothing, right? There. Now, a little bit noticeable because of course you're doing 500,000 computations. But I actually get an answer almost instantaneously. Let's ask old Wolfram Alpha here. What is 1000 choose 500? Just to make sure that we're correct. 270 and then it ends in 320. 270, 320. I'm convinced that it's correct. Right. Now, you could still get crazy. 10,000 choose 5,000. Now, how big is your tableau? How many zeros is that? 500 million? So now this is definitely going to be more noticeable. But it's probably still going to compute, even as I'm talking here, hopefully. But why? Why is it taking so much longer now? Think about this table. How is it growing? If I go an order of magnitude of 10 in both directions, then it's 2 dimensions. So how is it growing? It's growing in one dimension and another dimension. How complex is this loop right here? It's going to be order what? Order n times k, right? But we'll just go ahead and assume that k is half of n. Right? That's a good assumption because that's what I've been doing here this entire time. 10,000, half of that is 5,000. 10, choose 5, half of that is 5. Right? So this table, or the complexity of this is going to end up being order nk, and if k is order n, then this entire thing is going to be order n squared. Quadratic, right? It's still going here, so if it was 1 second before and now I've gone an order of magnitude 10 larger. How much slower is it going to be? 100 times slower is a good estimate. So it'll take maybe 2 minutes. We'll let it run. Okay. While we let that run, let's walk through what I did to arrive at that solution. Okay. So that's what dynamic programming is in a nutshell, right? What I'm going to do is I'm going to I'll phrase this as the FAST method. This is not my idea. This is somebody else's idea. In fact, I don't even know who to credit for this. But there's this FAST method, right? And sorry, it's F-A-S-T, all uppercase there, right? So the FAST method is an acronym. It's the first solution, right? It's the analyze the first solution. You identify, and here's where the acronym breaks down because they needed something that sounded good. Instead of F-A-I-T, fight, which is not a word, they said identify the sub-problems, right? And then you turn the solution around. So FAST, right? The process that I just went through implicitly was the FAST method. Well, first of all, several hundred years ago, Pascal came up with this identity, and so that part of it was done for us. It's basically identifying the subproblems. That if you want to compute this value right here, you can break it up into two subproblems that are slightly smaller. And then you've got these base cases here, right? That's the first solution, and then you analyze the first solution. You identify the subproblems, and then you turn the solution around. The turning the solution around is what I just showed you as new. Hopefully you've all seen, oh, there we go. It went 159, and then it ends in 120. All right, Wolfram Alpha, tell me if you can do this, because I did it.
What?
It's probably caching results. And there's more digits here. So 159, is that correct? What did it start out with?
We start with 159.
159, and it ended with 120? All right, more digits. More digits. More digits. All right, I'm giving up at that point. All right, but there it is, big. Okay. So anyway, the FAST method. What I did was I turned around the solution. Generally, these things are top down. That you take this problem and then you break it up into subproblems. Take those problems, you break them up into subproblems. Take those problems, you break them up into subproblems until you get down to a base case. That suggests a top-down solution that's all recursive. The turning around is looking at this recursion and viewing it as a table, like we did here with Pascal's triangle. Once you've got a table, then you can take out the recursion, and even the memoization entirely by looking at this table and saying, all right, well, this solution depends on this solution and this solution. So I have to compute these solutions first. That tells you how to fill this table out, top to bottom, left to right, diagonally, whatever. Whatever solutions this cell, you don't have to do any recursion, you don't have to do any memoization. You've turned the solution around. That's dynamic programming in a nutshell. You look for a recursive way of expressing the solution, and then you come up with a non-recursive way of analyzing the solution, of actually finding the solution, right? All right, so let's see. Let's outline those basic steps. Instead of just the acronym, let's go ahead and look at the basic steps. All right, from my perspective, at least. If you search for dynamic programming FAST, I'm sure that several articles will come up on it, and then you can read through their take on it. But here's my take. You identify a value that represents the desired solution / optimal solution to a problem. Now, technically here, there is some math involved. You have to have this optimal substructure property that says that you can, in fact, break this up into two smaller problems. And then the solutions of those two smaller problems mathematically give you a solution to the original problem. Pascal did that for us several hundred years ago, right? If you came up with your own solution, you'd have to come up with a mathematical proof that it's sound, right? You identify a recurrence identity in terms of smaller values of the problem, just like Pascal did several hundred years ago. And again, property. If this were, say, 423, 823, we would look into that in more depth, but this is just 310. So that's it. It's basically induction. You've seen induction before. You identify the potentially trivial base case. Right? You identify the desired final result. We did this with Pascal's triangle. We identified all of the base cases. What are the base cases? This column and all along the diagonal. We identified the final result. This is the one we want. So we're going to have to fill out this table in some manner. And then we came up with, well, this is dependent on this and this is dependent on this. That suggests that we can fill out the table left to right, top to bottom, or top to bottom, left to right. Right? Oops, over here. Right. And so you design that table. You design a table or tableau, if you want to be fancy about it in French, right? That holds values to each sub-solution. Right. Anybody speak French? No? Anybody take French in high school or here? No? Okay. All right. I was just looking for confirmation that I was right, that is indeed the French, coming from French. It is? Okay. You don't need to speak French to know that, right? You may need to keep track of additional data, in order to reformulate the solution. So what I mean by that is something that you've already seen. Floyd-Varshall's is kind of like a dynamic programming solution. And in that, we kept track of all of the weight of all of the optimal paths in our graph. But in order to build the path, we also had to keep track of the successor matrix. And so not only were we keeping track of the optimal solution, we were keeping track of the breadcrumbs that would allow us to build the optimal solution later on. And that's possibly something that you're going to have to do with some of these problems. With Pascal's identity, it doesn't matter because all we were doing was doing a number, right? If you actually wanted all of the subsets of that size, that's a different story, right? This was just a combinatoric thing of counting them. And by the way, do you have any hope of doing that? Could I have output all of these subsets of size 5,000 from a set of size 10,000? No, outputting those all is going to be, again, billions and billions and trillions of years. Okay? But counting the number of them, that's easy. Right? That's trivial. Anyway, you then design your loops to fill in the table or tableau so that the subproblems, the necessary subproblems, are available in a proper order. Right, then you fill out the table in the order you need to, right, whatever that means. Okay? Now, we're not going to have time to go over it, but I did assign remember the 0-1 knapsack problem? You programmed it, right? Okay, good. The 0-1 knapsack problem has a dynamic programming solution. What we're going to do probably next time is we're going to have to first go through this process here. We're going to have to identify a recurrence. The optimal solution to the 0-1 knapsack problem, where you're given this weight and all these items, is you can fill that out as a table, and you have to come up with some sort of a recurrence. Just to get you interested in it for next time, let's go ahead and define V sub I k, or j, excuse me. And I'm using two subscripts here to denote that it is actually going to be a table. And I'm just simply going to define this in English. This is the value of the optimal knapsack involving elements A1 through AI with a weight capacity of J. All right? So remember the input to the 0, 1 knapsack? You're given all these items, A1 through AN, with weights, W1 through WN, and values, V1 or V1 through VN. There we go. 1, 1, and 1. And then you're given this capacity. I think we use W, big W, right? And what you want to do is you want to steal as many items as you can, but the sum of all the weights cannot exceed the weight capacity here. And you want to maximize the value of everything that you took, right? So since you programmed this, I'm going to assume that you're well familiar with the problem. Good? Okay. So all I've done here is I defined what I want. I want the value of the optimal knapsack here. Now, what is the actual final solution? Final problem solution. What values of I and what values of J here, because given this definition right here, am I interested in? Just like with Pascal's triangle over here, I was interested in this one right here. When I became N, and when K became, well, and when J became K. So, what is the optimal value? Remember what the definition here is. It's the value of the optimal knapsack involving elements 1 through I. So, when I consider all elements, what should I be? N. Right? Because what are all the elements? A1 through AN. If you only want to consider A1, then of course that would be 1. If you want to consider A1 and A2, that would be 2. If you want to consider A1, 2, and 3, that would be 3. Right? Considering them all means that you end up considering N here. With a weight capacity of J, do I want to hamstring myself and say that I only have a capacity of 2? Or 0? Right? If I put 0 in here, then that sounds like a base case to me. If your weight capacity is 0 and you can't carry anything, what's the optimal value? 0. You can't carry anything, right? Get out. Right? Now I can carry 1 pound. Right? Now I can carry 2 pounds. Now I can carry 3 pounds. Dot, dot, dot. W would be my would be involved in the final problem solution. All right. So I have identified an equation that gives me what I want. I have identified the final solution that I'm interested in. What I need to do now is, 1, identify some base conditions, and 2, I need to identify how can I express this in terms of previous solutions. For example, if I've got, say, V sub 10 and 100, but say that N is equal to, like, there are 200 items in my knapsack, and my total weight capacity here is 1,000. In other words, I'm somewhere in between here. I've only considered elements 1 through 10. I still have 199 or 190 to go. I've considered an intermediate weight capacity. What if I could carry only 100? What's the optimal solution then? But ultimately, I can carry 1,000 pounds. Right? Yeah, yay me. Right? But given this, I need to find the value of this before I can work my way up to these things. So how am I going to express these two values in terms of smaller values?
Wait, why isn't 200 mean that the I value is just 10?
Well, it's intermediate. I'm going to work my way up.
Oh.
I'm going to go from I being 0, don't consider anything. 1, consider the first element. 2, consider the first 2 elements, ... all the way up to n. What is my j going to run?
All the way from
0 up to w. Right? But I need to figure out how I can compute one cell in terms of previously computed cells. And for that, we'll go ahead and wait until Monday. All right? Think about it, though. All right? How could you, what I'll do here is I'll give you a hint. I'm considering the 10th element. Previously, I considered 1 through 9. Okay. Now, I'm considering the 10th element here. I can take it, or maybe I can't take it. Or maybe I have a third choice. I can take it, but I choose not to. Right? So there are 3 conditions here. You can't even take it because taking it would exceed your weight capacity. You can take it, and you choose to do so, or you choose not to do so. Right? What are all of the implications with respect to these numbers here? All right. I will see you on Monday.
So is the I value